This short tutorial will demonstrate the use of a desktop process in the controller's manual mode. To review, a desktop process is nothing more than a process loop controller connected to a variable speed motor drive circuit, which drives power to a DC motor, which is coupled to another DC motor that acts as a tachometer, sending a speed feedback signal to the loop controller. So this way the loop controller is able to control the speed of an electric motor. So we're going to start by demonstrating manual mode operation. Currently, the controller is in manual mode. You can tell by the red light next to the auto manual button. We are looking at the output of the controller, marked by the letter V, which actually stands for valve. We could hit the display button if we wished and look at the process variable, the set point, or V for valve. So right now we're going to look at the output. And what I'm going to do here in manual mode is take the knob, spin it, and increase the output signal. As we do, it begins to drive electric power to the motor. And as we keep going further and further, eventually we drive enough power to the motor to overcome friction, and it begins to turn. I'm going to focus in on the motor right there. So now the motor has begun to turn. The motor is turning. It spins the other identical motor over here, which acts as a generator and provides a feedback signal to the controller telling how fast it's going. Now, this particular controller, like many industrial loop controllers, has a feature called set point tracking. When it is in the manual mode, whatever the process variable reads happens to be made the set point as well. So watch what happens when I adjust the output knob here. Remember the V display for valve. The output knob, as I adjust it, and we see this bar graph go up and down for my output signal, we're going to see both the process variable and the set point rise and fall accordingly. Watch. The motor is now spinning faster. You can actually hear it spin faster. That's because I've driven a stronger 4 to 20 milliamp current at the output of the controller. In response to that, the generator notes that the motor is spinning faster and sends a stronger voltage signal back, which gets read out as our process variable, or P. Because the controller is in manual mode and it has the set point tracking feature enabled, it automatically sets the set point equal to the process variable. The idea of this concept is that when you're in manual mode, you're adjusting the output until you get the process variable where you want it to be, and then when you're done doing that, you're probably going to switch to the automatic mode. And at that point, it is assumed that the process variable is already where you want it to be. So why not let's just make the set point equal the process variable at all times in manual mode, so that when you switch to auto mode, the set point's going to be right there where you left the process variable. That's the notion, that's the logic behind set point tracking. If we did not have set point tracking, what would happen in manual mode, as I raise and lower the output, is we would see a change in the process variable, but the set point would remain fixed at whatever level we last left it. That would mean, potentially, that after adjusting the process and having the process variable be at some value, switching to automatic mode may leave me in a condition where the set point and process variable don't match, in which case the controller would begin to correct and try to get me to set point. So the idea of set point tracking is based on the assumption that in manual mode I'm adjusting the process variable to a point where I want it to be prior to switching to auto, and so they make the set point track it. So here I go, manual mode, adjusting the output down. You can hear the motor spin slower. You can see the process variable bar graph go down, and of course because we have set point tracking enabled, the set point goes down with it. So I can bring the motor to a full stop if I wish. Output right now is about 20%, and due to friction in the motor, even though we're sending power to it right now, it does not have enough power to actually spin and overcome that friction. If I dial the output up, I overcome friction in the motor, it begins to spin, and we see that represented in the set point and process bar graphs that are now showing the speed of the motor. And that's a demonstration of the desktop process unit in manual mode. And one more thing before we stop the tutorial. We have it in manual mode right now, and I would like to show you what a load will do to the system. To introduce a load to the system, all I have to do in this case is simply reach down with my finger and touch the shaft that couples the two items together, the generator and the motor. When I touch that shaft, I impose a physical, mechanical load on the motor, and of course that is going to make it slow down. Since the controller is in manual mode, it will not take any corrective action. If it sees the motor slow down, it's not going to do a thing about it. So watch, I want you to notice this. When I slow the motor down with my finger, and you can see that as I reach over here, you're going to see the process variable bar graph and the set point bar graph dip down with the load. You will not, however, see any change in the output because we are fixed in manual mode. So go ahead and observe. Now I let go, and I touch the shaft, and now I let go, and I touch the shaft again. So you can see the effect of my finger physically loading down the motor, making the bar graph go up and down on process variable. No response is seen at the output because the controller again is in manual mode and is taking no corrective action.